Welcome back to the next video, everybody. Today we are going to be talking about constant group schemes. So first, let's talk about constant schemes. The idea here is to finally discuss the duality between x sub s and d of x sub s. So in other words, to finally realize capital D here as actually a duality of sorts. So let's let x be a set and let's let s be a scheme. The constant s scheme x sub s attached to s is given by the disjoint union over little x and big S of s sub little x. So it's just a disjoint union of copies s sub little x of s indexed by s. So each of these s sub x's here is just a copy of s. So there's one copy of s for each element of x. Okay, if T is an S scheme, an element f, let's say, in the T points of x sub s is, of course, determined by the collection of subsets u sub x given by f inverse of s sub x of T. These subsets are open, they're disjoint, they cover T. The restriction of f to u sub x is just the unique structure map u sub x to s sub x, which is isomorphic to s. Okay, and so such a covering both determines and is determined by the locally constant x-valued function phi on T that sends that neighborhood u sub x to the point x that indexes it. Okay. In other words, how do you summarize all this? The T points of x sub s are none other than the set of locally constant functions phi from T to x. So they're not just all functions, from T to x. They're the locally constant functions. And so if T is non-empty and connected, then the T points of x sub s, that set is just x, right? By basic topology. Okay, how about global sections of x sub s? Well, by definition of x sub s, the global sections on x sub s are relative to the structure sheaf O sub x sub s is just the product over x and x of the global sections on s sub x with the structure sheaf O sub s sub x. Okay, this is just how things work. This is how global sections work when you're looking at global sections on a disjoint union of schemes. Okay, you essentially end up with a product of the global functions on each piece. Okay, and this is, look though, since s sub x is just s for all x and x, what we're really looking at here is just the ring of functions on x with values in the global functions on s. So it's functions on x with values in gamma of s comma O sub s. Okay, and then from like basic scheme theory, we know x sub s is affine if and only if s equals spec r, let's say, is affine. Right? So x sub s is affine if and only if s is affine and x is finite. Or of course, there's the other case where r is trivial, but that's not interesting. Okay, and when this happens, you'll have x sub s is just spec a, because it's affine in this case. And a here is what? It's just the ring of r-valued functions on x. Okay, this should sound totally familiar if you've had even a semester of scheme theory. All right. So now let's move towards groups. What if x is a group? So suppose x is a group, then x sub s of T is now a group under value-wise composition of the locally constant functions phi from T to x. Well, that makes, this is functorial, so x sub s is a group scheme, right? And we call this the constant S group scheme. Okay, for good, hopefully you see why it's called that now. Okay, and you can readily check then that a section chi of the structure sheaf on x sub s is a character of x sub s, which was discussed last video. If and only if when viewed as a function on x with values in the global sections on s, like we talked about above, chi is actually a group homomorphism from x to the global sections on s, although, invertible elements. Okay, so not just a map from x to global sections, but a group homomorphism from x to global sections. All right, so now what if x is not just a group, but a commutative group? Then such a homomorphism chi is a point of dx now. Just by definition of dx, if you go back to my videos on examples of group schemes, you'll see that now we have something that's a point of dx, and it has values in s. And so what does this tell you? This tells you that the group of characters of x sub s is none other than d of x of s, the s points of d of x. And this remains true after base change from T to s. And so what's a quick way of saying all of this in one sentence? D of x base change to s is just the character group scheme of x sub s. That's it. And so hence the notation d of x. It's the dual of x. Right? If you think of characters as elements of the dual, like maybe from linear algebra or something like that, this makes perfect sense notationally and terminologically. Okay, well, it's also true, of course, as you should expect, that x sub s is the character group scheme of d of x sub s. It goes the other way as well. Okay, and so we have these pairings, d of x of T cross x of T to global sections on T cross, which we know, by the way, is just g sub m of T from a previous video. And what does this pairing do? It takes chi cross phi to, in quotes, chi of phi And by that, I mean, it's the section of O sub t, the structure sheaf on T, coinciding with chi of X on the set U sub X, which remember is phi inverse of X. And that holds for all little x and big X. Another way of saying this is that we have a homomorphism X of T to the Gur over T homs from D of X sub T to G sub M sub T. And this happens for each T. Okay, remember, we talked about this again in a previous video. These two statements are the same thing. Okay, let's say a little bit more about this to conclude the video. So a functor F, let's say from S scheme, from the opposite category of S scheme, so reverse the arrows, to sets is called a Zariski sheaf. If for each S scheme T and each covering T sub I of T by open immersions. I don't care to define all this right now, but just think of a topological space covered by open sets naively. Okay. The following sequence is exact. So we take F of T to the product over I of F of T sub I, and then we take this kind of double arrow map, this equalizer, to the product over I comma j of F of T sub I cross over S T sub j. And so what this is saying, if you translate this into ordinary sheaf language from like algebraic geometry, is, I mean, you want exactness in the middle here, right? So things in the image here should be exactly things in the kernel here. So what is that saying? That's saying kind of things here that agree on pairwise overlaps. So that would be things in the kernel of this map, because it's an equalizer. Okay, must come from something in the image of this map. Okay, so things here that are equal on pairwise overlaps come from a global section, right? Well, that's the usual sheaf condition from algebraic geometry, just written more generally. We don't have to look at topological spaces covered by open sets. We can look at like maps covered by open immersions, which are generalizations of that idea. And so you get a Zariski sheaf when you do that. And the point is that the above homomorphism here, it turns out to be an isomorphism for all T. And because both sides here, okay, because both sides are Zariski sheaves when viewed as functors, it suffices to check the affine case when T equals spec B. In other words, it suffices to check the case that when you take D of X and base change to T, you just get spec of, you know, the polynomial ring B adjoint X. And so that's how you would actually check this. And CSS page 131 gives a quick argument that this homomorphism here is an isomorphism. All right. All right. So we will keep progressing next time. And so thanks for watching, and I'll see you then.